Well, hi, this is Tim Duty coming at you again with another installment of Physics 3113, Thermal Physics and Statistical Mechanics. And this is Lecture 7, and today we're going to jump right into it and discuss what is known as quantum distribution functions. We'll develop those both for fermions and bosons, and then we'll move on to discuss fluctuations, and finally we'll go to the classical limit. So let's consider a system of n non-interacting particles. For now, let's say they're either fermions or bosons, and they will live in a container of fixed volume V, and this will be in contact with a reservoir temperature T and having single particle states labeled R, let's say. So for example, we might consider these states to be the particle in a box states that you found in quantum mechanics. So let's first consider the possibility or the case that the number of particles is fixed. That is, n here is fixed. Well, from what we've learned so far, of course, we could use the canonical ensemble to study this system in contact with a reservoir. And recall what that looks like. The canonical ensemble, or the canonical partition function, Z is the sum over all configurations that have a certain energy epsilon, and for each configuration we have this so-called Boltzmann factor, e to the minus beta epsilon. So for a system of non-interacting particles, the sum over configurations is quite easy once we specify the particle states. It's just a sum over numbers n1, n2, up to nr of this Boltzmann factor, which is just the number of particles in that state times beta. So because the particles are non-interacting, the energies add, and so this Boltzmann factor is quite simple. It's minus beta times the number of particles in state 1 times its energy plus the number of particles in state 2 times the energy of state 2, and so forth up to state R. Well, we've said we're going to fix the number of particles to be n, and so that means that these numbers, these little n sub r, we'll call that the occupation numbers. So the occupation numbers will be subject to the constraint that the sum over these occupation numbers has to equal large n. So in principle we could do that, but it turns out that this kind of constraint is quite complicated to carry out. It's quite complicated to carry out the canonical ensemble and calculate the canonical partition function with this kind of constraint. So last time, in the last lecture, we noted that for large systems, well, it really doesn't matter. We'll get the same results whether we use the canonical ensemble or the grand canonical ensemble. And in the grand canonical ensemble, of course, we have a chemical potential, and the number can fluctuate because the system exchanges particles with this reservoir as well. But the point is, we can use this, and in the limit of large n, it will get the same results. The only complication is that in doing that, we'll have to adjust the chemical potential to fix the mean total number of particles here, and we'll have to do that to equal n. We'll see how that works. I should say at this point that this technique is used a lot in physics. For example, if you ever get to the point where you're studying the theory of superconductivity, you'll learn about the so-called BCS theory, named after Bardeen, Cooper, and Schrieffer. And if you look at their, original paper that finds the so-called BCS ground state for superconductivity, they do just this same kind of trick. They use this same technique. That is, they move to the grand canonical ensemble and play this game as well to help them solve the problem of superconductivity. So it's a very interesting technique, and it's quite useful. Okay, well, let's start with fermions. So fermions obey, of course, Fermi-Dirac statistics. And so this occupation number of state R, n sub r, can only equal 0 or 1 for every R. Now at this point I should say we're going to ignore spin for the moment. So that's why we can only have 0 or 1 particle in every state. We'll ignore spin for the moment. It's very easy to put that in down the road a bit. So in this case, it's very easy to evaluate the grand sum because you'll see here that this sum over the occupation numbers will only have two terms, a term with n sub r equals 0 and a term with n sub r equal to 1 for every r. So this sum is very simple. It just has, for each value of r, it just has two terms, a 1 and this term when we have one particle in that state. And so that's easy to do, and we just have this sum over r. So that's the answer for fermions for the log of the grand sum. In contrast, for bosons, of course bosons obey Bose-Einstein statistics. This occupation number can be anything from 0 to infinity. So if we write down the log of the grand sum for bosons, we still have these two sums here. Sum over occupation numbers for the different energy levels, and sum over occupation numbers, and then sum over energy levels, of course. And at first that looks like rather complicated, but then we realize, we look at this sum and we realize we could factor out the term without the occupation number, and we realize that this sum here is actually an infinite series. That is, it has the form, this sum over occupation number has a sum, is an infinite series of this form. Recall, if you remember an infinite series, the sum s equals sum n to 0 to infinity of some term x raised to the nth power. And you'll see if we let x equal the exponential of minus beta epsilon r minus mu, then this will be our infinite series. And of course, the magnitude of x is less than 1, and so this sum the infinite sum has a finite answer. That's just 1 over 1 minus x. And so we plug this x back in there, and we see this sum can be done. And here's the answer. I've just changed here where I had see epsilon minus mu. I've just changed that around and got rid of the minus sign there. So then we can put that inside here, and we find that for Bose-Einstein statistics, the result for the log of the grand sum is just this term here. And if you look, it looks quite similar to what we found for fermions. It's just that we have a minus sign here and a minus sign there instead of the plus sign. So if we want, it's very easy. We could just write this in an inclusive way, that log of the grand sum is plus minus sum over r log of 1 plus minus e to the minus beta mu minus epsilon sub r. We're still summing over r. And of course the plus sign is for Fermi-Dirac statistics for fermions, minus sign for bosons. And so we found the log of the grand partition function, and we can go off and now calculate some things. So for example, we could find the mean value of the occupation of state R, this quantity here. And of course we showed this in a prior lecture, that the mean n sub r, or the mean occupation number of state R, is just given by minus 1 over beta times the partial derivative of log z with respect to epsilon sub r. And if we just operate on this result with this derivative, we see we calculate the mean occupation number of state R. So it's just this 1 over e to the beta epsilon r minus mu plus or minus 1. I've done a little bit of, so just I left out a couple steps, but I operated on this with the derivative, and then I multiplied the top and the bottom by a factor to get a 1 on top and to get it in this form. And so that's the answer for the mean occupation number, plus sign for fermions, minus sign for bosons. And I should say, usually you think of this mean occupation number as a functions of the energy here. Once you've specified the temperature, or beta, and the chemical potential. So you think of this as a kind of function, and so because of that, this mean occupation number, this result, is also called a quantum distribution function. So I'll use that terminology as well. I'll say distribution function, and you'll know what I'm talking about as the mean value of the occupation number. And it also, you'll see a lot, and I'll do this as well, in many cases, we'll just drop the subscript r and think of this occupation number, a mean occupation number, as the distribution function for a state with energy epsilon. And so, when we'll go to use it, of course, we'll remember that we have an index there, or we'll end up doing a sum or an integral, but we can just think of this distribution function n and write it this way, which of course depends on mu and kBt, and sometimes I'll just write k, drop the subscript t, or usually I'll just use beta. And so this then is our distribution function for mean occupation number for energy level epsilon, once beta and the chemical potential are specified. Okay? So for most of this lecture, though, I'll keep the subscript r there, just to remind us what we're doing, where we're headed, and even though I might not say, I might just say occupation number, or mean occupation number. Okay. Okay, so just looking at this, then we see that there's quite a difference between Fermi-Dirac and Bose-Einstein statistics, and it comes out for this mean occupation number in terms of this sign here. It's a very big difference. We'll see how that works. And we'll also find very different behavior of the chemical potential for fermions as compared to bosons. Okay, so let's go back and look at fermions in more detail. So we found the mean occupation number is equal to 1 over e to the beta epsilon minus mu plus 1. And so, as I said at the beginning of the lecture, we want to keep this mean total number of particles, which we're just going to be a little bit sloppy and call n from now on, understanding that we're working with the grand canonical ensemble, and then at the end the fluctuations in this are very, very small, so we'll just call it n. We want to keep that fixed, and we'll see that in order to do that, we'll have to adjust the chemical potential, or the chemical potential will be a function of temperature, that is. So, and what we'll find, we'll explain in more detail, that at low temperatures, mu for fermions is positive and large compared to kBt. Well, it should be a capital there, sorry. And for high temperatures, mu for fermions will become negative. Let's also just think about the behavior of the mean occupation number for different epsilons relative to the chemical potential. Let's look at this formula here. So when epsilon is much, much less than mu, that is the energy of this state, is much, much less than the chemical potential, then this basically becomes 1, right? Let's take a minute to understand how that works. Okay, so we're measuring energies from the absolute lowest energy in the system, which is where a 0 is. So that means this epsilon sub r is always positive, but when it's much, much less than mu, then this quantity is negative, and if we go to low enough temperature, then beta is getting very, very large, and so this factor is going to become 0 in this limit. And then, of course, we just have 1 over 1 equals 1. In the other limit, when epsilon sub r gets much, much greater than the chemical potential, then it's easy to see this factor gets really large, and so the denominator is getting very, very large, and this becomes, the mean occupation number becomes 0. And of course, if epsilon sub r is set to be equal to the chemical potential, then the mean occupation number is, of course, 1/2. So actually, it's good to plot this for a few values of kBt and look how it works. So here's the plot. And so what I've done here, here's the mean occupation number, and here's the energy. I've scaled the energy by the chemical potential to make this sort of dimensionless just for convenience. And I've made plots for different values of mu divided by kBt. So here, very, very low temperatures, then this value is very large. So this is sort of approaching 0 temperature, and then this is increasing the temperature. And you can see that at very, very low temperatures, I get this step function. And so what this tells us that we imagine we have this system of many particles, many fermions, and we start and we put one in and it takes the lowest energy state, and we put another one in and it has to take the next higher state, and so forth. And when we get to n particles, we have that last nth particle has some energy, and we'll call that the Fermi energy. Now, it's very clear then to see what the chemical potential has to be, because of to satisfy this distribution for the number of particles we have, then mu has to be equal to the Fermi energy, so that this distribution actually describes the system of n particles with a specified Fermi level. So basically, the Fermi energy here depends on how many particles we have, because they have to they can't occupy more than one state. So this is a very simple example that shows how you have to set the chemical potential to get the number of particles. So this is at very, very low temperatures, of course, at 0 temperature effectively. Now we see what happens as we turn up the temperature. Then this step becomes broadened, and basically it says that down here there's only partial occupancy, or in this region there's only partial occupancy of the states and the effective temperature. That's the effective temperature. So at finite temperature, we only observe partial occupation of the states near the Fermi energy, which of course is equal to the chemical potential. Okay, think about how that works. Well, what we'll find is at very high temperatures, the chemical potential decreases, and then it becomes negative, and then the distribution changes dramatically, which we'll see later. So this argument really only works at 0 temperature, right? Okay, and we'll come back in more detail with fermions in the next lecture. The next couple of lectures, actually. All right, let's consider bosons now. So just to remind you what we found the mean occupation number of state R, or the mean occupation number depends upon the energy in this way, 1 over e to the beta epsilon sub r minus mu, and the key thing was the -1 here. So in contrast to fermions, or Fermi-Dirac statistics, where mu is large and positive at low temperatures, we'll find that the chemical potential for bosons is always negative, or at most close to 0. And the reason why we need this to be always negative, if you look at this formula, is that we want this needs to be positive, definite, for all values of energy, even down to epsilon, what we call the ground state. Here we'll measure everything from the lowest energy, the ground state, for 0. So even if that's 0, then you can see that if mu were positive, this number could swing negative below 0. Right. So that's why the chemical potential for bosons is always negative. And what we'll see that as we go to very, very low temperature, it gets very, very close to zero. And also what you can see from this formula is that more than one particle can occupy a given single particle state R. So this can be larger than one, obviously. Okay. And what we'll find is that the chemical potential for bosonic systems, once again, it's a function of temperature. Remember, we want to maintain this constraint that we fix the mean total number of particles. And that means the chemical potential has to be a function of temperature, and it becomes very close to zero as t equals 0. And in fact, it's really not that we have to, fix the mean total number of particles. In a physical system, sometimes that's fixed for a number of reasons. Okay. Well, we'll see this has important consequences, such as what's called Bose-Einstein condensation. That's a really, really interesting effect, and we'll study that actually, I believe, next week, in lectures next week. Okay, so at this point we're going to move on to fluctuations, but before we do that, let's take a little breather. So we'll just have a couple minutes breather. You can get up, stretch, walk around, make yourself a cup of tea, and come back in just a couple minutes. Okay. Well, okay, and welcome back. And now we're going to discuss fluctuations from the quantum distribution point of view. Now, in the last lecture, we noted that fluctuations in energy and total particle number are extremely small in the grand canonical ensemble when we go to large number, of course, which is, what we're usually interested in. But today we're going to examine particle number fluctuations for the ideal Fermi and Bose gases, given what we've already learned. And we will be interested this time in fluctuations in mean occupation number for the individual states of energy labeled by R. Now, we don't really need to separately study fluctuations in energy in this situation, that is, for non-interacting gases or quantum systems, because in fact, we only need to look at the fluctuations in mean particle number, and that's because the energy, in particular the mean energy, is just a sum of all the states of the mean occupation number of that state times its energy. So once we have fluctuations in mean occupation number, we automatically will get this by just summing up things. So we get the fluctuations in energy for non-interacting systems sort of for free. So let's consider the variance of the mean occupation number of state R. That's given by this quantity. We take the mean of the occupation number squared of state R. We subtract the square of the mean occupation number of state R, the usual thing for a variance. And then we can find the standard deviation if we want by taking the square root. So, of course, we've already derived in the first part of this lecture the mean occupation number of state R. Once you find the grand sum, you can find that by taking this derivative, multiply by minus 1 over beta, and as we showed, we get this plus sign for fermions, minus sign for bosons. Okay, so we've done that, so we have that term already. We just square this, right? What about this term? So to find the variance, we need to find this term here. And if we look at that, we can convince ourselves by going back to the definition of the grand partition function, and we'll see just as if as in a similar manner to that you can find the mean occupation number with a first derivative, you'll see right away that you can find the mean occupation number squared by a second derivative. And of course we divide by 1 over z, and we have this beta squared here. Well, I mean, in principle that's the answer, but unfortunately in this form it's actually not very useful. In fact, we'd like to get this term, we'd like to get this in terms of the logarithm of the partition function. And why would that be? If I had a class, right, if I were lecturing in front of you, so I'd stop and I'd ask someone why. So maybe you can think about why. I mean, it really is a practical reason, actually, because we found that the log of the grand sum, fermions or bosons, is a sum here over R of factors like this, rather than a product, large product over R. And that's just much easier to work with when we take derivatives or do anything. In the future lectures, we'll find that we'll go to the continuum limit, and like we have particles in a box, and we have a very large box, so the energy levels get very close together, and this will become an integral, and we'll be able to work with the log of the grand sum here. So it's just a practical reason. So how do we do that? Well, first thing we do, let's just see what we get if we take the second derivative of the log of the grand sum with respect to epsilon r squared. Let's just do that, since we know we have a nice expression for this, and see what we get. And if you do that, you see, find this identity. That's just product rule. And you have these two terms. And you look at these two terms and you say, of course this is just, well, this one you could already easily convert to, you can easily see this term here is just the square of this term, and we'll see what this is. We probably recognize that already, but let's look at this term. Oh, well, that's kind of what we had to start with if we multiply by 1 over beta squared. That is, go back here. You see, we had the second derivative of the grand sum with respect to epsilon r squared, and we have 1 over z, and we just have 1 over beta squared. So all we have to do is, if we multiply everything by 1 over beta squared, we'll get precisely this term, right? So we'll do that. We'll multiply by 1 over beta squared, and then we'll move this guy over here, and we'll identify what we've got as the mean occupation number squared, and we'll see. And I've just multiplied by 1 over beta squared, identified this term as this, and moved and just flipped it around this way, and we still have these two terms left. And you see we're almost there, because now this is in derivatives of log of the partition function. And you look at this and you go, oh, I recognize that term, right? That's just the mean occupation number quantity squared, right? Because, well, just as we know here, where did we go? Here, right? If we square that, we get, the minus sign goes away. We want 1 over beta squared times this quantity squared. That's just this, right? 1 over beta squared. So, and now we have, look, we have exactly what we want. The variance is going to be this term minus that term, and so all we get is this term, right? So it's gotten quite simple. But the interesting thing is we can simplify it even further, because as we recognized here, this derivative, 1 over beta times this derivative, is just this guy, is just the mean occupation number. So now we've got the variance here in a quite simple form. It just says that the variance, which is the mean of the occupation number squared minus the mean occupation number, with the mean occupation number squared, is just minus 1 over beta times the partial derivative with respect to epsilon sub r of the occupation number, mean occupation number of state r. So it's a bit of work, but it's a quite simple answer. And since we have this already evaluated for fermions and bosons, then we just have to take that derivative. Just to remind you again, that's what we found, plus sign for fermions, minus sign for bosons. We take derivative, we use the sort of chain rule, and we'll find just this, right? And you look at that and we'll say, well, we're going to assume this term, the partial of mu with respect to this energy, one of these energies, we just changed one energy of the state. You know, we have a lot of states involved, right? So changing one of those is, you know, probably not going to do much. So we'll assume it's negligible, which is generally a good approximation. So we get rid of that term. And then we find then that the variance is basically equal to this here. We still got this downstairs. We have this term upstairs. And it's still, we'd like to simplify this a bit more because this is starting to look, this somehow is mean occupation number quantity squared. So let's both add a 1 and subtract a 1, or subtract a 1 and add a 1 here, and we'll break this into two terms, right? We'll call this one term, and then we'll make that another term here. And then you can see what we're getting then is we have the same thing up here as here, so that one term cancels out. That's just, of course, the mean occupation number. And then this term over here that's left is just the mean occupation number squared. And of course, we just make sure we keep track of the signs. And here, the minus sign is for fermions, and the plus sign is for bosons. So we see this rather interesting and simple answer then, that the variance is mean occupation number minus for fermions plus for bosons, the square of the mean occupation number. And that's really simple. So if we want, we can look at the fractional variance, or so we're anticipating we're going to take the square root of this. So we'll divide by the mean occupation number quantity squared, because eventually we're going to want to take we're going to get the fractional deviation. And we see we can do that, and we get here. So we get 1 over mean occupation number minus or plus 1. And that's a really interesting result. Let's think about that for a bit. So for fermions, minus sign, we found that at comparatively low temperatures, that is for temperature much less than, say, the Fermi energy, which at low temperatures is the chemical potential, that the occupation number was almost exactly 1. Almost exactly 1, except for states very close to the chemical potential, the Fermi energy. How close? Well, it depends upon temperature, but so very close for low temperature. And so if this is 1, you see that the sorry, if this is 1, this is nearly 1 minus 1. This quantity is almost 0, right? So this shows that for fermions, fluctuations are vanishingly small for most states, except, you know, near the Fermi energy. And that's, of course, what we expected. I mean, if you go back and look at the plots, should we go back and look at the plots? So I'm going to scroll back and look at back here. When you can see at low temperatures, there's going to be, not only is this going to be 1, but there's going to be very little fluctuations. And of course, if you have fluctuations, you'll have some average less than 1 here for fermions, right? That's all we're saying. So that actually makes a lot of sense, right? Right. Now for bosons, however, this occupation number is going to can get much larger than 1, actually larger than 1, especially for the low energy states, as we've discussed, right? So these fluctuations can become quite large. When this gets really large, that term goes to 0, and we have that then the fractional deviation would be like the square root of 1, which is 1. So fluctuations are same order as the occupation number. That's a large fluctuation. Of course, the large fluctuations in boson occupation numbers, occupation states, of course, is associated with this tendency of bosons to clump in the same low energy state. And we'll see that that also leads to this Bose-Einstein condensation, which we'll discuss. Now, one thing we need to mention, though, is even though for bosons in particular that the fluctuations in the individual states can be large, so fluctuations in particle number or mean occupation number for bosons in a particular state can be very large. Fluctuations in total N, as we've argued before, are still really small. That is, the fractional deviation from N divided by N, that is, so the deviation of N divided by N, fractional deviation, of course, is always order 1 over square root of N. And this is easy to see. I mean, so remember, large N is the sum of the occupation numbers of all the states, and we're going to consider the situation where you have a very, very large number of states eventually, and that means we're adding a bunch of random variables that have finite variance, and it might not be the same, but it's finite for each state, and so in the end we're always going to have a fractional variance in the total number that's going to go 1 over root N, and that's just really a sort of law of large numbers, central limit theorem itself. Okay, well that's our discussion of fluctuations in occupation numbers. Let's now use what we've learned in this lecture so far, and we're going to study the classical limit. So at very high temperatures, as you can see from the mean occupation number, or the distribution functions, as they're called, you can see from the distribution functions that the mean occupation number is much, much less than 1 at high temperatures for both fermions and bosons. And this is then the classical limit. And if that happens, if this is really, really small, then you'll find that the fractional occupation is going to be, well, let's just go back to this formula. If this gets really small, this term dominates. We can ignore the 1, the plus or minus 1, because this term is going to be huge, and then you'll see that if I take the square root, the fractional variation, the standard deviation divided by the number of state R is going to be 1 over square root of that, right? That's just what that says. So we always have this for total number, but in the classical limit, which is high temperatures, then we'll have this for each and every energy level. Okay. Now, we've mentioned this a couple of times, that for a fixed number of particles N, which is sometimes something for convenience, but sometimes it really is fixed. So let me think of a situation. Suppose you have a solid and you're looking at electrons in a solid, and you have N, ions, then most likely you're going to have N electrons, because it's going to cost a lot of energy to have, depending on the size of the system, it's going to cost a lot of energy to have an extra charge or missing a charge. So anyway, fixed number of particles, we have to have this condition that the sum over the states of the occupation numbers has to be N, and that will determine what the value of the chemical potential. And we showed that at t equals 0 for fermions, which was quite easy. We'll discuss more examples of this later and in detail, but let me just summarize what we're going to find. So for fermions, mu is positive as low temperatures. As we saw, it has to equal the Fermi energy at t equals 0, and it decreases with increasing temperature, and it becomes negative at sufficiently high temperatures. For Bose-Einstein statistics, as we said, mu is always negative, and that's because we want to ensure that the mean occupation number is positive for all energies, including epsilon 0. So it's always negative, but it approaches 0 as t goes to 0. And we also find that the values of the chemical potential for fermions and bosons or for both statistics, converge at high temperatures. And we'll show this in the next plot. It's in the textbook as well. So here you see a very low temperature chemical potential for Fermi-Dirac statistics is the Fermi energy, and for bosons it's really, really close to zero. And then as we raise the temperature, the fermion, the chemical potential of fermions crosses zero, goes negative, and they both approach the same value up here at high temperature, which is the classical limit. So we can get a better idea of this by looking at, we'll introduce a new concept here. So once again, we have the distribution functions given by this formula, plus for fermions, minus for bosons. So let's introduce an exponential function of the chemical potential. We'll call it lambda. Lambda equals e to the beta mu. And so if we do that, we can look at this factor, we can pull out inverse lambda, lambda to the minus 1, or 1 over lambda, inverse lambda. And this lambda is called fugacity. So then we could write the occupation number here is like this, 1 over lambda to the power minus 1, or 1 over lambda, which is just e to the minus beta mu. You see we take e to the minus beta mu out here, and then we have e to the beta epsilon sub r, and then plus or minus 1. This, again, is fugacity. So in the classical limit, the chemical potential for both situations is large, becomes large negative and large magnitude. And that means this fugacity, or the inverse fugacity, becomes very, very large. So fugacity becomes very, very small, and so its inverse is very, very large, much, much greater than 1. And so if this denominator becomes much, much greater than 1, this term is much bigger than 1. And this means, of course, the occupation number, mean occupation number, gets really, really small because the denominator is getting large. But secondly, this term dominates, and we can conclude that that's negligible compared to this term. And then you see we have a simple result that in this classical limit, the mean occupation number of state R is lambda, the fugacity, times e to the minus beta epsilon r. Now, we have the constraint, right, that the sum over the occupation numbers, sum over the energy levels of their occupation numbers, has to be the total number of particles in, and that tells us essentially what this fugacity is. We just have to just plug that in there, and you get this, right? And therefore, we can write the mean occupation number of state R as, plug in the value for lambda, and we get n times this factor here. And you just say, aha, I recognize that factor. It's this probability. It's precisely the probability that I'd get the so-called Boltzmann probability, that the probability I'd get for the occupation of that state, if I was using a canonical ensemble. And so if that's the probability and I have large n particles, then I'll find that many particles on average in that state, if that's the probability to be in that state. See? So that's kind of interesting. So let's think about that. Now, we'll come back to this, but it starts to look familiar. Now, remember we found the log of the grand partition function, log z here. For fermions and bosons, we found this, just to remind you what we had. And now I'm just going to plug in, I'm going to use this lambda to write it this way with the lambda out here. That's equivalent to what we found before. Now, if we know the grand sum, we can find the partition function, the sort of log of the partition function, the canonical partition function, which is this quantity. Because remember, we found this result that for large n, we had this result that log of the canonical partition function would equal the log of the grand partition function minus beta mu times n, right? Or just plugging that in here, plugging that in here, we have this. And so plus sign fermions, minus sign bosons. So in the classical limit, as we argued, this fugacity gets really, really small. And so we can expand the logarithm in here, each of these logarithms. So we'll expand this. And just to remind you that if we do Taylor series for logarithm 1 plus some small quantity, this is going to be a small quantity because lambda is small and this is always less than 1. Then so log of 1 plus some small quantity x is just x. Somehow I got that written twice for some strange reason. Anyway, we get this. So we get the log of the canonical partition function is just plus or minus lambda sum over r e to the minus beta epsilon r minus beta mu. Here we still have this term. And we plug in again what we found for lambda, and we see that that cancels, and we just get, that just becomes total number of particles in. This becomes minus beta mu in, and we look, oh right, wait a minute, we had this definition of lambda, right, because lambda equals e to the beta mu. In other words, log lambda is beta mu. So we could write this term as n minus n log lambda, right? This is log lambda, and that's n log lambda. Let's just plug lambda in again. What we found for what lambda had to be based upon the constraint on total number of particles. We write it this way, or just writing it all out as different terms. We have n minus n log n plus n times this factor. And so, oh, well, you know, you can use Stirling's approximation in reverse, basically. And so we'll find here then that that becomes minus n factorial. And then, of course, if we, you know, exponentiate this, we have, wow, how about that? We got that z is 1 over n factorial times product over of this raised to the power of the total number of particles. And so this is basically our partition function for, sorry, canonical partition function for one state, or one particle, let's say. And we can imagine our one particle can be put in each of these levels. And we have z to the large n in factorial. And so we see this now looks just like the canonical ensemble. We took the classical limit of quantum distributions, and we get this factor. Remember last lecture I mentioned this factor of n factorial, which accounted for the indistinguishability of particles in a gas and avoids overcounting that you would do if you assumed that, you know, particles in a box obey or are classical, and then you could put labels on them, right? I could say I have particle 1 and I have particle 2 and I have particle 3, and I count all the states by having all those configurations, and that's not correct with quantum, according to quantum mechanics. And this mystery factor that, as I mentioned, was quite controversial in the early days of statistical mechanics, before just that, while quantum mechanics was sort of being figured out, comes out of this limit naturally. Okay, so that's it for today's lecture, and I'll let you think about this again, and I'll pick up with the next lecture. In the next couple of lectures, we'll go into more details about fermions. Okay, so have a good one. Don't get too far behind on this course because there's a lot of material here to learn. So try to keep up with the lectures and tutorials and also and so forth. And we'll see you next time. Oh, and by the way, if you're still listening, that song I'm calling the new Fermion Blues because, well, let's face it, We all have to act like fermions these days. Maybe one day we'll get to be bosons again. Anyway, have fun and good luck with the studies.